So the second talk is again a Berkeley talk. This is on pushing Middleboxes into the cloud. This talk is actually going to be given by Justine, who just finished her second year at Berkeley. Her advisor is Sylvia Ratnasamy, and she likes to make problems someone else's problem. So.
Hi, everybody. So as mentioned, my name is Justine. I'm a graduate student at Berkeley, and today I'm going to talk about some work we did on Middleboxes. This, of course, is a collaboration with my colleagues Shadi Hesson and Colin Scott, who are graduate students at Berkeley, with Arvin Krishnamurthy from the University of Washington, with my advisor, Sylvia Ratnasamy, who's at Berkeley, and with Das Secker from Intel Labs. So to start, let's just talk about typical enterprise networks. You have some number of end hosts, desktops, laptops, they're user-facing devices. And then you have some number of servers. Maybe they're running the company website in a small local data center. All of these devices, they connect to the network by a number of switches, and the switches connect to a router, which connects the enterprise to the outside world, the internet. Now, in addition to these traditional networking devices, the routers and the switches, network administrators also deal with a variety of network appliances, or Middleboxes. And these devices include things like firewalls, intrusion detection systems, web proxies, WAN optimizers, and load balancers. And at this point, our diagram is getting pretty complicated. And our intuition looking at a picture like this is that managing the network itself is complicated as well. But to really get to the bottom of why this is complicated and how Middleboxes impact network management, we wanted to dig a little bit deeper. And so what we did was a survey of 57 enterprise network administrators, and they represented a wide range of networks. So the networks were small, some with less than 1,000 hosts, and others were very large, with hundreds of thousands of hosts and tens of sites around the world. We asked each administrator about their deployment size, their expenses, the complexity of their network, and the failures they encountered. So the first question we asked was just, how many Middleboxes do you deploy? So what we see here is a box plot. Each cluster represents a category of device, and each type of box plot represents a different size of network. So the purple box plots represent the smallest networks. These are the ones with 1,000 hosts or less. And the red box plots represent the largest networks. These are the ones of 100,000 or more. And the green and blue fall somewhere in the middle. Note that the y-axis is in a log scale. So the key thing to note about this plot is that across the board, the box plots just line up. Right? The number of Middleboxes is typically on par with the number of routers and switches. So this tells us that as our networks are growing bigger and bigger, not only are we deploying more and more routers and switches, we're also deploying more and more Middleboxes. Now, to look what this looks like in a little more detail, we asked the administrators what kinds of Middleboxes they deploy. So this box plot is exactly the same as the previous one, only now we've broken down the Middleboxes by the type of device. There's a number of firewalls, a number of WAN optimizers, a number of proxies, etc. And the first thing we notice is not the value of the number of devices, but that there are so many kinds of them. And when we step back and think about what this means for management, it means that there's a wide range of expertise that we need to manage them, right? Firewalls are these security devices, and proxies are these performance-oriented devices. So the skill set you need to manage one device is different than the skill set you need to manage another. Anecdotally, one of the companies we talked to had entirely different teams for each class of device. There was one team that managed the firewalls, another team that managed the proxies. To look a little bit more at this management impact, we asked exactly how many networking personnel each enterprise had. So here we see on the x-axis the number of Middleboxes, and on the y-axis the number of personnel. So the number of personnel for a given network ranges from 1 or 2 administrators for the smallest networks to hundreds for the largest. So not only does this confirm that manageability requires large staffs and is thus very complicated, it also adds another layer to our perception of cost of Middleboxes. Not only have we seen that there are lots and lots of devices, all of which cost tens of thousands of dollars a piece, but the average salary for a network engineer in the United States is somewhere between $60,000 and $80,000 a year. Digging further into this administration question, we asked how administrators spent their time. And one of the things that they spent their time doing was dealing with failures. So most administrators spend between 1 and 5 hours a week dealing with failures, and 9% spent between 6 and 10 hours a week dealing with failures. When we asked what caused these failures, overwhelmingly the most common reaction was to describe disconfiguration problems. So for 67% of network administrators, they said that the most common cause of failure for firewalls was just misconfiguration. Even for the experts, the ones who are commanding $60,000 to $80,000 salaries for their skill sets, managing middle boxes is an extremely error-prone endeavor. For the latter two the second most common cause of failures were overload and physical and electrical failures. So overload simply means that there was simply too much traffic offered to the device and it couldn't handle it. And physical and electrical failure means that there was just a hardware outage or a power failure. Now, the thing that's interesting about these latter two causes of failure is that the way that we typically deal with them is by adding redundant hardware. But we know that middle boxes cost tens of thousands of dollars per device. And a result that we show in the paper is that middle boxes as deployed are typically only moderately utilized. So it's not clear that it's a cost-effective solution to simply add more devices. Okay, so I just walked through some of the results from our survey. There are a lot more details in the paper, but let's recap what we've learned. First, we saw that middle boxes impose high capital and operating expenses. High capital expenses in that there's lots of devices, they're quite costly, and high operating expenses in that they require large administrative teams to manage them. We saw that this management question is time-consuming and error-prone. There are lots of people dedicated to managing middle boxes, and even the experts have lots of misconfiguration problems. Finally, we saw that physical and overload failures are also substantial sources of problems, but we weren't sure whether adding redundant hardware was really going to be a cost-effective solution. Now that we understand the problem in detail, we can step back and ask how we can improve this. So one option would be to think about how we can re-architect middle boxes within the enterprise internally. And this is a track that was taken by some work last year in NSBI with COMB and in NSBI the previous year with ETTM. But a different track, and that's the one that we're going to take today, is to propose that we just get rid of the middle boxes altogether. So our proposal is to take a network that looks like this, remove all the middle boxes, and place them in the cloud instead. Now, this proposal is sort of appealing for a number of arguments that we've heard about why people move their computation and storage to the cloud. When it comes to high capital and operating expenses, the cloud brings with it the benefits of economies of scale and pay-per-use. When it comes to management being time-consuming and error-prone, the cloud can simplify configuration and deployment because administrators only deal with an abstract representation of a middle box service. They're not configuring specific devices or worrying about where to allocate capacity. Finally, when it comes to physical and overload failures, the cloud can provide redundant resources for failure, but now at the amortized cost of a large cloud provider rather than the upfront investment available to enterprises. Okay. So I just presented to you some descriptions about the challenges with managing middle boxes and networks, and we propose moving to the cloud. I want to talk about our design. It's called APLOMB, but before I dig into it, let's mention some of the challenges in designing APLOMB. First, we want to have only minimal complexity at the enterprise. So if we're going to move all these middle boxes to the cloud, we're going to need some sort of redirection layer, we're going to be bouncing traffic all over the internet, and this has the potential to be quite complicated, and maybe even more complicated than the middle boxes that we sought to outsource in the first place. So one of the key design goals that we have is to make sure that our design is simple. We also want to achieve functional equivalence. So what this means is that for a given device that we might want to deploy in an enterprise network, we should be able to get most of the same benefits, but by deploying it in the cloud instead. Finally, we want to make sure that we only impose a low performance overhead. One of the key hindrances to good performance is going to be latency. So by bouncing traffic to and from these data centers, there's the potential that we'll inflate perceived latency and impact application performance, and we want to avoid this at all costs. Okay, so without further ado, our solution is called APLOMB. APLOMB stands for an appliance for outsourcing middle boxes, and it's an extremely simple design. I think the best way to describe it is just to walk through an example. So here we've returned to our enterprise. We've brought our servers. We've moved all of the middle boxes now to the cloud. With APLOMB, the enterprise administrator deploys a special APLOMB gateway at the egress to the network. So this gateway maintains a tunnel to and from the cloud, and naturally this tunnel is encrypted. And now, whenever any traffic comes from a host within the enterprise out to the outside world, when it reaches the egress of the network, it traverses this APLOMB gateway, where it's encapsulated and sent directly to the cloud. At the cloud, the packets traverse a series of middle boxes according to whatever policies the administrator specified. They then go out over a NAT, where the source address is rewritten to the IP address belonging to the cloud. This way, any return traffic will be directed right back to the cloud, where it can receive ingress processing and then go back through the tunnel back to the enterprise. So with this simple redirection layer, just using the APLOMB gateway and the NAT, we've enabled redirection just for this lower class of devices. It's not too different from what they experience today. Right, so the end host, the desktops, the laptops, the traffic is typically already NATed, not only to save on address space, but for the security benefits of being inaccessible to outside traffic. But for this top class of devices, the servers, we do want to be accessible to incoming requests. So for these, we're going to have to use the DNS in order to redirect incoming requests to the cloud. What we do is we have the enterprise administrator register all publicly available services with the cloud provider. So here she's registering a domain name along with the IP address of the device. And then the cloud provider registers that domain name on the enterprise's behalf. But instead of registering it with an IP address that belongs to the enterprise, it registers it with an IP address that belongs to the cloud. It then pre-populates that IP address into the NAT at the cloud provider. Now, when a user on the internet does a lookup on the domain name, the traffic goes to the cloud provider, where it receives middlebox processing and is sent back to the appropriate devices. Okay, so that's how the redirection layer works. Now that we've talked about how we achieve redirection, let's go back to this performance question we were concerned about, the latency issue. Now, the way that we deal with latency in cloud services is traditionally to just take advantage of the fact that data center providers have multiple data centers around the world, and they're strategically placed to be close to their clients. This is what we're going to do, much like normal cloud services. We're just going to make a slight tweak to how we select which data center to route through. Where normally an enterprise should route to and from the data center that minimizes its RTT. What we want to do is we want to route through the data center that minimizes the end-to-end latency. So instead of minimizing the latency from the enterprise to the data center and back, we want to minimize the latency from the enterprise to the data center, to an external client, back to the data center, and then back to the enterprise. Now, the thing to note here is that the best data center, then, is not necessarily the data center that's closest to the enterprise. It might be the data center that's closest to the external client, or a data center that's somewhere in the middle. This also means that the best data center for talking to one client might not be the same data center as the best data center to talk to another. So the APLOMB gateway is going to have to maintain multiple tunnels. It keeps a simple routing table in order to select between these tunnels, but it's not really a routing table in the BGP sense. It's more of just a lookup table that maps from internet prefix to tunnel endpoint. And this lookup table is populated by a controller at the cloud. So every data center at the cloud periodically issues measurements to different prefixes on the internet, much like they do for optimizing CDNs. But they send these reports back to the cloud controller who selects optimal routes for all of the enterprises, and then pushes these routes to the controllers or to the APLOMB gateways at the enterprise. Importantly, never is the enterprise administrator involved in this process. It's completely seamless to them. All of the complexity is managed by the cloud provider. Let's return really quickly to caches, though. I talked about how we were redirecting to minimize end-to-end latency rather than RTT to and from the data center. Of course, for caches, we actually do want to minimize the RTT to and from the data center. So we bias the data center selection algorithm to select data centers that are closer to the enterprise, but only for traffic that's going to traverse a caching service. So to summarize, that's APLOMB. APLOMB stands for an appliance for outsourcing middleboxes, and the way it works is we just place middleboxes in the cloud, use APLOMB and the DNS to redirect traffic to and from the cloud, and that's it. Well, okay, there are more details in the paper, but in essence, the design itself is very simple. Returning to our goal of functional equivalence now, we can look back and see whether or not APLOMB achieves one of our core goals. Can we, for a given middlebox that we want to deploy in the enterprise, deploy in the cloud instead? So here we have some of the most common middleboxes that we saw in our survey. For firewalls, IDSs, load balancers, and VPNs, we can indeed outsource them. When it comes to proxies and caches and WAN optimizers, things get a little bit more complicated. These devices exist not only for some latency performance benefits, they also exist to minimize bandwidth. Caches store content locally within the enterprise so that if there's a popular file that hundreds of clients within the enterprise are trying to pull, we can save on the bandwidth of pulling it hundreds of times by just storing it locally. If we place the cache outside of the enterprise, we lose out on that benefit. Similarly, WAN optimizers save bandwidth. They do this by compressing traffic. So they compress all traffic to and from sites of the same enterprise. And if we compress traffic after it goes over in the egress link, we've kind of missed the point. Now, it's worth noting that in our survey, we saw that WAN optimizers are extremely unpopular with small networks, but they're extremely popular in the largest networks. These are the ones with hundreds of thousands of hosts or more. If we want our solution to be general, which we do, we should address these, but this is a smaller fraction. So for these networks, we introduce APLOMB Plus for compression. And all we do here is we just add a generic compression layer to the APLOMB gateway. And all it does is some simple redundancy elimination before the encapsulation step. We don't go so far as to implement a full WAN optimizer. We just do some very basic redundancy elimination. But as I'll show later, we find that this gives fairly good performance. So assuming that APLOMB Plus can resolve some of these bandwidth issues, we've now resolved our functional equivalence issue. Okay, so let's talk about some other questions we have about this design. I'm going to move into the evaluation, and there'll be two sets of questions that we want to answer. The first set of questions are about the performance of APLOMB from an application standpoint. What's the latency we get? How's my application going to run? Am I going to notice that I'm being redirected through the cloud? The second two questions are going to be questions that administrators care about. Is this worth doing? So part of how we're going to evaluate is with our own deployment. We built and deployed APLOMB. We use EC2 as our cloud provider across 7 data centers. We use OpenVPN for tunneling and Data, which the previous guys used as well. It's an open middle box virtual machine that deploys multiple middle boxes within a single device. So we deployed all of this on EC2, and then we had 2 types of clients that we ran back at Berkeley. So we had a software VPN client that we ran on our laptops, took home, used ourselves, and then we also built a tunneling software router so that wired hosts could plug in with no configuration and have their traffic tunneled to and from the cloud, much like we would imagine they would experience in the enterprise environment. But beyond using our deployment, which we could use to get performance metrics, we also used 2 other mechanisms to evaluate APLOMB. We used some wide area measurements because we were very concerned about getting good network latency. And we also did a case study of a very large enterprise. So one of the enterprises that we talked to in our survey gave us a bunch of extra data that allowed us to answer some more questions about what the impact would be on a large enterprise that outsourced all of its middle boxes to the cloud. So, first question, does APLOMB inflate latency? What we see here is a CDF of latency inflation between Planet Lab nodes with and without redirection. So we took 2 base latency measurements between pairs of Planet Lab nodes. The first latency measurement was their base latency over the internet. This is their normal round trip time. We then took a second measurement, which was their latency with redirection through the best EC2 node. So this is the EC2 node that minimizes the round trip time between the 2. We then subtracted one from the other, and this is how we calculated what we called inflation. What we see here is that for 60% of these Planet Lab pairs, redirecting through EC2 had a negative inflation. That is, there was a net improvement by redirecting through EC2. Now, for those of you who know about triangle inequality violations in the internet, this is a very intuitive result. But we also wanted to look at an enterprise footprint rather than a university footprint. So we repeated the same experiment, but this time with the enterprise data set. And here we saw that we also had fairly good performance, but that in the median case, we did see some inflation. And this inflation was about 1.13 milliseconds of the overall RTT, which in terms of wide area latencies is typically considered to be fairly negligible. Further, the sites that did experience inflation were primarily in areas where EC2 did not have a very wide footprint. And presumably, were EC2 to expand into these regions, their performance would improve. So we just talked about latency and saw that we had some minimal penalties for the performance with latency, but applications also depend on other good quality metrics for their network connections, like bandwidth or jitter. I'm just going to give you 2 data points on the bandwidth and jitter question. These come from our deployment and our usage with APLOMB. So first, bandwidth. We stress tested our implementation by running BitTorrent downloads over APLOMB, and we saw that our download times increased on average only 2.3%. We also ran a number of VoIP calls over APLOMB, and we found that the jitter over these VoIP calls was consistently within industry standard bounds of 30 milliseconds, and that the calls came through quite clearly. So I just walked through 2 questions related to application performance, the quality of the network connection they're going to get over APLOMB. Let's talk about some questions that the administrators care about. First, does APLOMB negate the benefit of bandwidth-saving devices? So we were worried about removing our WAN optimizers and switching to this generic solution, and there's going to be some overhead for that. Let's calculate what it is using the case study of the large enterprise. So what we see here are a series of bar graphs. Each cluster of bars represents a different site of the same enterprise. So we have a North American site, an Asian site, all the way to a European site. On the y-axis, we see a normalized 95th percentile bandwidth value. And the purple bars are the first thing we're going to look at. These are the aggregate traffic from that site going to other sites of the same enterprise. So this is our base value. Today it goes through a WAN optimizer. The blue value shows this traffic if we remove the WAN optimizer and routed the traffic through APLOMB instead. Now, with APLOMB and removing the WAN optimizer, the bandwidth consumption inflates about 50%, which is a noticeable overhead. Now, when we move over and look at the red bar, APLOMB Plus moves this back down, but there's still a slight performance penalty. So in the median case, moving from a WAN optimizer to APLOMB Plus had a penalty of 3.8% inflation. And in the worst case, it had an 8% inflation. So this is a moderate penalty for the intra-domain traffic. This is the traffic from one site to another. It's worth noting that much of the enterprise traffic today does not go over WAN optimizers already. It goes to and from web services or other cloud services. This traffic is not going through a WAN optimizer today, but it would go through some compression with APLOMB Plus. For this fraction of the traffic, we would see a performance benefit, but unfortunately we didn't have the traces to evaluate how much. Another question the administrators might care about is what are the benefits they're going to get from elastic scaling? So we talked previously about overload as an example of one of the common failures in networks. And we said that a common way to resolve overload is just to add more devices, but we weren't sure whether it was going to be cost effective. So we then argued that moving to the cloud would be great because then we could use extra middle boxes when we needed them, but scale back and only pay for what we needed most of the time. So the benefits from elasticity in the cloud are going to be very strong if peak consumption is much higher than the normal case. What we see here is a bar graph. Once again, this is some sites of the enterprise. And on the y-axis, we're showing the peak to mean ratio. So this is the peak traffic over the average traffic for each of the given sites. And we have the total traffic and the HTTP traffic. So in normal cases, for most of them, they're somewhere in between the 1 to 2x range. But for others, the peak to mean ratio is much higher. In the worst case, it's as much as 13 times more traffic at peak hours of the day than in the average case. So for this site to avoid overload entirely, they would have to provision 13 times as many middle boxes as they would need normally. With the cloud, they can elastically scale up to 13 times as many middle boxes and then drop those when they're not using them. So at least for this latter site, the benefits from elasticity would be great. So I just walked through some evaluation. I'm going to recap the results. I showed some good application performance, that there was a negligible overhead in terms of application performance with the APLOMB. Our median latency inflation from a real enterprise was 1.1 milliseconds, and our download times using BitTorrent increased only 2.3%. We also saw that generic redundancy elimination saves on some of the bandwidth costs, and that we had strong benefits from elasticity for many of the enterprise's sites. So to conclude, I hope I've convinced you today that moving Middleboxes to the cloud is both a practical and feasible solution to the complexity of enterprise networks. I just showed you APLOMB, which is an extremely simple solution, yet despite its simplicity, it managed to outsource most Middleboxes with only a minimal performance impact. Thank you very much.
Great talk, thanks. If you can go back, this is Sagar Guha, Microsoft Research India. If you can go back to your slide with the 6 types of middleboxes that you guys focus on, 3 of those are squarely security. There's VPN, I think, IDSs, firewalls, and one of those, the load balancer is 50% security, maybe to protect the DOS attacks, right? So the question is, when you move stuff to the cloud, do you end up making your security problem someone else's problem, or you end up additionally taking on their security problems as part of your enterprise security problems, right? So you not only have to worry about a guy in your parking lot with a high gain antenna, you have to worry about a guy in Amazon's parking lot with a high gain antenna. Insiders in your enterprise as well as Amazon's enterprise, right? Malware in your enterprise as well as malware in, say, Amazon, or for that matter, Microsoft, Google, right? Anyone's enterprise where your admin assistants or the receptionist is running weird stuff on their computers, right? So have you looked at, or have you asked these administrators that you guys polled whether they're okay taking this additional security risk for moving all these middleboxes to the cloud?
I have kind of a funny story about that, actually. So you're exactly right. This is the same problem as pretty much all other cloud things. You're trusting the cloud provider to do a good job. But when I talked to one of the administrators about moving the security devices, and particularly moving his servers to the cloud that required extra firewalling, he was really excited about this because it meant that if it was a failure or some sort of security breach, he wouldn't be the target of the lawsuit. It would be Amazon's fault.
So let's keep the questions and answers brief. Hi, Srinivas from Princeton University. This is a very interesting one. Thanks. I have a question on, so do you have some thoughts on the business case from the point of view of the cloud provider for this? So, and a second quick question is, do you also have some thoughts on the privacy implications of this from the point of view of administrators and the enterprises, for instance? Thanks.
So when it comes to the privacy concerns, it's basically the same story as we've been worrying about with the cloud. It hasn't stopped the cloud from being very popular. You have to trust the cloud provider. Enough people have trusted the cloud provider to make it extremely successful for computation and storage. But if you ultimately cannot trust Amazon or will not trust Google, this isn't going to be the solution for you. In terms of the business case, I'm not a startup student, I'm a research student. But I do know that as we were doing this work, we started talking to some more people around the Bay Area who were starting to do startups in this space. So there's a company called Ariaka that offers this just for WAN optimization, and there's another company called Zscaler that's doing this just for intrusion detection. So I'm kind of following them to see if they scale out and add more middleboxes the way that we envision that they will.
Hi, Roque again of Cisco. So if you go back to the list of companies and size, correct? Mm-hmm. Question for me, because you focus basically on, from the list of boxes, you focus on a subset related with the internet access, correct? There's a lot of those middleboxes which are also used internally on the WAN, MPLS, whatever kind of WAN network they have. So from the list of companies that you have, how many of them are single internet access? You only have one internet access, one connection to the world? How many of them were multi-homing, or do you got that data?
So if you look in the paper, so the smallest enterprise, I would guess, are not multi-home. This is just guessing. They have less than 1,000 hosts. They're one administrator kind of shop. For the largest enterprises, they have sites all around the world. An office in Helsinki and another office in Dublin.
Correct.
So it's not even possible for them to be single.
Yeah, it's a long tail list.
Providers.
But the thing is, for those which are with only one connection to the internet, right? I mean, at the end of the day, this is managed access, firewall, security, mainly service, correct? And ISP has been trying to get into or doing managed services for 15 years or something. So what's the difference between for them to hire cloud provider, just do it with their upstream provider?
So one of the benefits that you don't get from this managed locally business is the capacity benefits. So I showed the elastic scaling benefit. You would still have to provision your hardware for your peak capacity if you were doing a managed services solution. That said, you do get some of the manageability benefits in that somebody else is going in and dealing with the nitty-gritty of configuring it. So they have some similar benefits, but there are some benefits that they don't get, and one of the big ones is just elasticity benefit.
Maybe 2 more questions, and just no follow-up questions, just one question.
Henry from Columbia. There's a company called Total Uptime that provides the 3 services that you list for, I think, $49 a month. So
oh, wow.
I've used them. The issues with those, but that you didn't cover. But this seems to be fairly well. I mean, it's commercial technology at this point. So
Total
I'm a little surprised that this is considered all that new.
Is that a question?
Yes, I'm asking for a comment.
I mean, so if you go through and read the paper, I would say that the contribution of it, I mean, first of all, it hasn't been published before. This is at least new to us. I'm glad that you've heard of Total Uptime. But the other thing is that
I'm not affiliated with the company.
Yeah, we go through and we very thoroughly evaluate how it works, whether or not it's feasible for an enterprise. In the paper, there is some discussion about what a cloud provider needs to be able to provide good service, and really, how much of a footprint does the cloud provider need? What kinds of enterprises can use this? What are the typical problems enterprises have that are solved by this? And I'm sure that industry people have done, some market research on this, but we've done like a thorough end-to-end analysis of the technical questions behind it.
So one last question.
Aaron Gember, University of Wisconsin. Does this work for middle boxes not at the border of your network? And do you have a sense of how many of those there are?
So for middle boxes not on the border of the network, I'm presuming you're talking about like firewalls. I have a backup slide for you. So what he's talking about are these firewalls. We call them internal firewalls in the paper, and they protect hosts within the network from other hosts within the network. They're really worried about security. Often these are deployed for things like PCI compliance, where I'm storing credit card data on one server, and I really don't want the employees in my network to access that server. And so I have these firewalls on the inside. And you're right in noting that APLOMB actually can't outsource these firewalls because they have to sit right next to the device that they're protecting. There's two good news on that front. The first good news is that many of these devices are moving to the cloud, so the servers themselves are going to the cloud, and with them, the middle boxes move. So that's not APLOMB moving them to the cloud, that's the trend of the servers moving to the cloud, moving them to the cloud. The other thing is that with routers becoming more and more configurable, you can adopt this off-by-default kind of architecture, where if you say, oh, I don't want the sales network to be able to talk to the data center network that stores the servers, you can just say that in the routers and filter it without needing to have any complex middle boxes there.
Let's thank the speaker once again. Okay, the final talk of the